At the end of this video, you should be able to explain how shapes of molecules are accounted for by hybridization theory. Chapter 6, Section 5, Hybridization. VSEPR theory is useful for explaining the shapes of molecules. However, it does not reveal the relationship between a molecule's geometry and the orbitals occupied by its bonding electrons. To explain how the orbitals of an atom become rearranged when the atom forms covalent bonds, a different model is used. This model is called hybridization, which is the mixing of two or more atomic orbitals of similar energies on the same atom to produce new orbitals of equal energies. Methane, CH4, provides a good example of how hybridization is used to explain the geometry of molecular orbitals. The orbital notation for a carbon atom shows that it has 4 valence electrons, 2 in its 2s orbital and 2 in its 2p orbitals. We know from experiments that a methane molecule has tetrahedral geometry. How does carbon form 4 equivalent tetrahedrally arranged covalent bonds by orbital overlap with 4 other atoms? 2 of carbon's valence electrons occupy the 2s orbital, and 2 occupy the 2p orbitals. Recall that the 2s orbital and the 2p orbitals have different shapes. To achieve 4 equivalent bonds, carbon's 2s and 3 2p orbitals hybridize to form 4 new identical orbitals called sp3 orbitals. The superscript 3 indicates that 3 p orbitals were included in the hybridization. The superscript 1 on the s is understood and not written. The sp3 orbitals all have the same energy, which is greater than that of the 2s orbital, but less than that of the 2p orbitals, as is shown in figure 6-23 on page 188 of your text or on the screen now. Hybrid orbitals are orbitals of equal energy produced by the combination of 2 or more orbitals on the same atom. The number of hybrid orbitals produced equals the number of orbitals that have combined. Bonding with carbon sp3 orbitals is illustrated in figure 6-24a on page 188 of your text or on the screen now for a molecule of methane. Hybridization also explains the bonding and geometry of many molecules formed by group 15 and 16 elements. The sp3 hybridization of a nitrogen atom, which has a configuration of 2s2, 2p3, yields 4 hybrid orbitals. 1 orbital containing a pair of electrons, and 3 orbitals that each contain an unpaired electron. Each unpaired electron is capable of forming a single bond, as is shown for ammonia in figure 6-24b. Similarly, 2 of the 4 sp3 hybrid orbitals on an oxygen atom, which has a configuration 2s2, 2p4, are occupied by 2 electron pairs, and 2 are occupied by unpaired electrons. Each unpaired electron can form a single bond, as is shown for water in figure 6-24c. The linear geometry of molecules such as beryllium fluoride, which is BeF2, again, see table 6-5 on page 186 of your text or on the screen now. That linear geometry is made possible by hybridization involving the s orbital and 1 available empty p orbital to yield sp hybrid orbitals. The trigonal planar geometry of molecules such as boron fluoride, BF3, is made possible by a hybridization involving the s orbital, 1 singly occupied p orbital, and 1 empty p orbital to yield sp2 hybrid orbitals. The geometries of sp, sp2, and sp3 hybrid orbitals are summarized in table 6-6 on page 189 of your text or on the screen now.
The model that describes the rearrangement of electron orbitals in covalent bonding is called hybridization. For example, the carbon atom contains 4 valence electrons, 2 in the 2s orbital and 2 within 2p orbitals. In terms of energy level, it looks like this. In the formation of methane, these orbitals will hybridize into sp3 orbitals. The hybrid orbital has an energy level between those of the original orbitals. The name sp3 comes from the fact that 3 p orbitals are combining with a single s orbital, as shown here. These hybrid sp3 orbitals result in the tetrahedral shape of the methane molecule. Hybridizations yield different molecular geometries, as shown here.
At this point, you should be able to explain how the shapes of molecules are accounted for by hybridization theory.